Hello again. This is Math 2233 coming to you from the College of DuPage, and the title of this lecture is Kepler's Laws and Such. And as always, please be an active listener as you watch this video. So we're going to be talking about Kepler's laws. Kepler's first law can be stated: a planet moves in a plane, and we will prove that, but we also prove that a planet moves in a plane along an elliptical orbit with the sun at one focus. That's called Kepler's first law. Kepler's second law states that the position vector from the sun to a planet sweeps out area at a constant rate. And Kepler's third law may be stated as: the square of the period of a planet around the sun is proportional to the cube of the average distance between the planet and the sun. Now here are some little pictures showing some of this stuff. So here you see the elliptical orbit around the orange sun, and this could be the Earth, although the Earth doesn't have quite that eccentricity. It's more closely, most of the eccentricities are more close to a circle. And over here, what you see is that there are strobe lights going at equal time, and you can see that it does carve out equal areas in equal time. So that means when you're close to the sun, you get bigger slices. The angle changes more than if you go out here, but you see the area of each of these slices is the same. There is a wonderful app at this website. I'll refer to that later, and I would encourage you to go to that and look at this. But this is what Kepler's laws say. Let's begin deriving them then. So consider a Cartesian coordinate system with the sun at the origin. And that's important because the sun does have to be at the origin for this to work, but you can let the sun be at the origin because you get to choose the coordinate system. And you let the order triple x, y, and z denote the position of a planet in three-dimensional space. Now those are functions of t, so that changes over time. We define the position vector then, r is going to be xi plus yj plus zk, where ij and k are the vectors that we know and love. And the velocity is going to be the derivative with respect to time of those. Now here we're using Newton's notation, where we put dots on top of those x's, y's, and z's to make these be the derivatives with respect to time. And of course ij and k are the unit vectors in the x, y, and z direction, respectively. And then we'll take the next derivative, and again we'll get x double dot I plus y double dot j plus z double dot k. And so now we have expressions for the r, the v, and the a in terms of x, y, and z and the unit vectors. As happened in history, we're going to derive these using Newton's laws and show that Kepler's laws, all three of them, must be true. So one of Newton's famous laws of motion was that the net force is equal to the mass times acceleration. This is sometimes called Newton's second law. And here, mass, the m, is the mass of the planet, the lowercase m is the mass of the planet, and F is the force on the planet. And Newton also had a law of universal gravitation. And the law of universal gravitation said that the force, well, in fact, we need some definition here. So if r hat is a unit vector in the r direction, then Newton's law of gravitation applied to a planet, and the sun is given by F, the force vector, is equal to minus g, that's the universal gravitational constant, the mass of the sun times the mass of the planet, divided by r squared, and that's the scalar multiple of the unit vector r hat. But r hat is r divided by the scalar r, and so if we make that substitution, we have F as this. So if I equate this equation with this equation, after all they're both F, then what I can do is I can cancel out the mass, the lowercase m, on both sides, and I conclude And we're neglecting the gravitational force due to the other planets, but we're canceling out the lowercase m. We get the acceleration, which we know to be r double dot, is equal to minus g capital M over r cubed times r. Now let me state that another way that's very important. The acceleration is a constant multiple of r. Therefore, it is parallel to r. And we're going to use that very soon. Now we are going to finally prove that the planet moves in a plane. So we're going to take the derivative of, with respect to time, of r crossed with v, the radius crossed with the velocity. So when we take this using our product rule, we're going to have the derivative of the first, which is going to be v again crossed with v, plus r, the first, times the derivative of the second, which is going to be a. But you see, this one is going to be 0 because a is in the same direction as r. That's what we just talked about on the previous chart. And so that's what we have. And v crossed with v, well, the vector crossed with the self is also going to be 0. So you see, we conclude that this derivative with respect to t is 0. That means that r cross v is a constant vector. That means that r and v lie in the same plane because there's a vector that is perpendicular to both of them. So r and v lay in the same plane, and the planet moves in a plane. Now we move to do Kepler's second law. We will choose our coordinate system so that k is in the direction of h. We're free to do that. And we will then represent the constant that we had, h, which was r crossed with v, but this is now going to be, since it's moving in the direction k, it is some scalar h times k. We'll use that in a bit, and you want to remember that equation. So here is the area that is being swept out, and you can see that the area is this sector, but it's very close to being this triangle that I see here, and that is a right triangle. And so what we're going to do is we're going to use that approximation and take limits. So since the area OAB, and I'm showing you it again over here, is approximately equal to the area of the triangle OAC for small theta, and since the length of line AC, look at the drawing, is approximately r times delta theta, that's the area of a circular sector, and the length of the line OC is approximately r, we can say that that change in area that happens when you move that is approximately 1/2 the base times the height. And so when I put that all together, it is going to be delta A is approximately equal to 1/2 r squared delta theta. Now I'm going to divide both sides by delta t and let delta t approach 0, and I will get A dot is equal to 1/2 r squared theta dot. Now, since the planet moves in a plane, and we've already established that, we can talk about polar coordinates. And so we're going to say that r is xi plus yj. By using polar coordinates, that is r cosine theta I plus r sine theta j. And those are the polar coordinates. But now we're going to take the derivative of this with respect to time, and it's important that remember that r is a function of t, it changes, and theta is also a function of t. So we're going to be using the product rules and the chain rules. When you do that, and you should verify these calculations, you have that the velocity is equal to the first time derivative, but it ends up being this when I've simplified this with respect to I and j. Now what I'm going to do is I'm going to recall that h was equal to r cross v is hk, but I can calculate r from this expression, and I can use this for v, and I get this, that h is equal to this. That's what we find in the k direction. You should finish these calculations, but that is what you get. And when we simplify that and we use the fact that many things, I cross j is k and j cross I is minus k, it follows that A, and it follows from actually this equation where we had A dot was equal to 1/2 r squared theta dot, that A dot is equal to that, and that is also h then, using this equation, over 2. But h was a constant vector, so its magnitude is constant, so the derivative with respect to time is constant. That means that the change in area with respect to time is a constant. That means the change in area in equal times is a constant. This is Kepler's second law. Turns out this is a good place to pause, so now, more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and each other. May God bless you all.